we get the recording going and say once again, 2 o'clock meetings, always. Let's see, sometime in the next month, I'm going to be traveling, but I'll try to arrange it so that I can still have our usual Zoom times. Well, I haven't really looked at that. We may have to shift a time or a day because of that, but I'll still be able to keep up with everything, I think. Let's see. We're missing Kevin. Well, anyway, let's have a look at where we were. I was just talking with Tyler before the rest of you got here about where we're headed. But for today, I want to say a little bit more about gauge theory. Let me just review. The review is on the board. Great. Let's just run through this a second. So how we construct our gauge theory. Now, so we start with a group quotient. So what we want to look at is the direct product of the Poincare group with whatever group or groups we want. So for the standard model on curved spacetime, right, we could put SU3 cross SU2 cross U1 here. And all we have to do to put that, whatever group this is on the fiber, is also put it in the subgroup. Again, as a direct product, the Lorentz group, direct product of Poincare with Lorentz group gives us space-time. It gives us Minkowski space, unless we modify it. Then the SUN here, we'll leave that, as I said, on the fiber. The Maurer-Cartan equation is equivalent to the Lie bracket. Take this form. So you have this form for the Lorentz transformations. Then for the translations, you get an orthonormal frame field here, the solder form, Vierbein, Vielbein, depending on what dimension you're in and so on. But that rotates as a vector, so you get or transforms under Lorentz transformations as a vector. This is the form of an infinitesimal Lorentz transformation. So yeah, it's easy to see what this equation means. You've got some orthonormal frame field, possibly different at each point. When you move infinitesimally from one point to the next, you get an infinitesimal Lorentz transformation that brings you to the correct new frame at that nearby point. So it remains orthonormal. So all you get is a Lorentz transformation. You don't get a general coordinate transformation as you would if we were doing a Christoffel connection and the general linear group. Okay, and then you have the Lie algebra of SUN, or this could be whatever internal symmetry group you like. It's an internal symmetry group principally because these generators are direct product. All of these generators commute with all of the Poincare generators. It's interesting to think about what makes a gravitational gauge theory different from any gauge theory, like an SUN gauge theory. The thing you have in relativity that you don't have in these other gauge theories is basically a potential for the potential. The connection is derivable from the metric, hence the Christoffel or the spin connection, either one. But there's this underlying level that describes distances between points that you don't have for SUN or whatever gauge group. So anyway, these are the Maurer-Cartan equations. Then we generalize the connection. We keep this structure, but we change whichever of these gauge fields we're interested in studying. if we want to keep our theory on flat space, we don't mess with omega and E. We leave that as the Lorentz manifold, but we could do all this in curved space just as well. Well, no, not just as well, much harder. Kevin. But we could set up the structure in a curved spacetime, and by changing these connection forms, we would add some two forms here. If we only generalize the connection of the internal symmetry, then we're going to add a two form F here for each generator of the symmetry Lie algebra, the internal symmetry. So with electromagnetism, we just had one field here. With SU2, we have three different field strengths. With SU3, there would be 8. And these would correspond. For SU2, these will be the W and Z particles. For SU3, there'll be the gluons. And those will couple to various spinor fields in whatever ways we set up. So the Yang-Mills field strength becomes a two form. We can express that either in the orthonormal basis or a coordinate basis. Either one is fine. We can do everything we like with either of those. Then the physics enters when you write an action. I think you can still see. Let me tip this just a tad further. You write an action for a typical Yang-Mills field. The action is going to be some combinatoric times F wedge dual F. This, if you expand the forms and look at what you've got, is just Fi mu nu contracted with Fi mu nu. So we're summing over the different fields that we've introduced by this procedure. And then each is fully contracted the way you would contract the Faraday tensor with itself to write the Maxwell action. So very similar to Maxwell, but you've got a bunch of them and they couple to one another. So then we can ask if we also include here a coupling to some current, then we can show that that current is conserved. And we ran through that last time. Now, last time I asserted that something that looked like a normal covariant derivative really was a covariant derivative. I identified certain things that came up as covariant derivatives. I'd like to talk a little bit more about that today to show you where that comes from. Okay, following this, let's see, I'm now looking at page 321 in the book. That might be a little different than what you're seeing because I've been working on the book a lot this last week. I've got, let's see, 322. So yeah, I'm up past 350 now with some cool new stuff that you'll like. But before we get to the stuff that you like, let's talk about those covariant derivatives. You guys doing okay with the differential forms? Again, this is sort of new stuff, but not impossible to digest fairly quickly. Now, what I want to talk about is the connection, and that is I can do this. I can do this for any Lie group. So let me take a step back away from this summary and look at the Lie algebra and the Maurer-Cartan equations for a general Lie group. Were there any questions on this summary? I think we went through this last time.
Just double checking the star is the Hodge star, right?
Yes, that's the Hodge. Yes, correct. And my definition of the Hodge dual is given in the gauge theory notes, which I've put on the Canvas page. I put a link to the gauge theory notes on the Canvas page. And one of the preliminaries there is differential forms. And if you're wrestling with sign conventions and normalization conventions, you'll see mine there. You will see different forms of that. So let's start with the generators of some Lie algebra. And this gives us some structure constants. One thing you see variations on is the position of the third index on the structure constants. Sometimes it's last, sometimes the one contracted here is first. And it doesn't make a whole lot of difference. You just use whichever or move it if you prefer. Then to get to the Maurer-Cartan equations, we define dual one forms, dual in this sense. So for in a coordinate basis, these would be dx's and those would be ddx's, basis for tangent vectors and basis for the cotangent space and coordinates. Those give a Kronecker, and this g and that omega are just some linear combinations of the dx's and the ddx's. So we start with some basic duality like this and take linear combinations of these to produce those, which makes the coefficients of these inverse to the coefficients of those. And that's how we're able to derive the Maurer-Cartan equations, which take the form of differential equations with structure constants coupling the basis forms together like this. So this is the Maurer-Cartan equation. Now, the Lie algebra, let me think. Well, I'm going to do some, sorry, go on. What was the question?
Yeah, you said that it looks like a differential equation. So could you like usually find the sheaves, basically like the flows or the basically the forms that would solve these equations?
Yeah. Yeah, what solving these equations is basically equivalent to finding the group elements. So whereas with the generators here, we would exponentiate and that would take us on some curve out into the group away from the identity element. Integrating these differential equations is much the same thing. Now, these objects are going to turn out to be connection forms. And that's what I want to show you today, how those have the properties of a connection. So
small detail.
Yeah.
Do these forms always follow the Frobenius theorem, or do they sometimes not?
Yeah, if you break these into, as you often do, into different kinds of transformation, if you want to solve these, yeah, you can use the Frobenius theorem wherever it applies here. This equation is involute. That is, d of this omega closes into the omegas on that side. That tells you that there exist coordinates dx mu. So if you've got n of these a's, you're going to have n of these coordinates. And if you hold x mu equals constant, that puts you on a submanifold, not a very interesting one if these span the whole space. But if we're doing a gauge theory like we were last week, the Frobenius theorem is really useful because you can, well, yeah, the the basis equation, this one, is this is an involution on E, which means I can find some coordinates. And now if we're, let's say A runs 0, 1, 2, 3. Am I writing large enough to see here? So we can find 4 coordinates. This is not spanning the whole space now. But if we hold X constant so that E is 0, that solves these equations. 0 equals 0. Okay, that's good. We now have the remaining structure equation here spanning the rest of the Poincare group. Well, having E equals 0 now puts us on submanifolds, right? We've basically collapsed the manifold, and now we're looking at a particular fiber. That fiber is a manifold described by this remaining equation. And that's an involution too, so we can work with that involution. But the collapse to a fiber is using the Frobenius theorem. And that fiber is a submanifold of the full group manifold. If you do it the other way, because this one's in involution, now you collapse to the space-time manifold spanned by the E's. So you can use it either way. Now here on the fiber, if I choose some coordinates on the fiber, these are going to be 6 parameters that span the Lorentz group. Probably is convenient to write these in an adjoint representation. So we've got some matrices BC. And those are Lorentz transformations that take you up and down the fiber. Okay, returning to Maurer-Cartan. There's a slick way to write these. Yeah, let's if I take omega, right? We've mentioned that these are Lie algebra valued 1 forms. Well, if I write them in the basis for the Lie algebra, I'm putting the generator back here. This makes this with the linear representation. These are some matrices, and those act as a linear representation of the group, or the Lie algebra. This omega is a 1 form, so this is a Lie algebra valued 1 form, omega, and you can get very condensed with this notation. And I'm going to play with this a little bit today. If I look at omega wedge omega, where omega is this Lie algebra valued thing, this is not 0 because I'm anti-symmetrizing the generators. What this really is omega A GA wedge omega B GB. Remember, there are a bunch of omegas buried inside this symbol. So if I pull these out, wedge omega B, the forms anti-symmetrize. So I'm imposing an anti-symmetrization on these G's, and I can make that explicit. This is going to be 1/2 the commutator of the G's. And half that commutator, there you go, Kevin, is 1/2 omega A wedge omega B. And then this is a structure constant, C sub, let's call it CAB here, GC. So we're back in the Lie algebra with a structure constant on the omegas and the factor of 1/2. And that lets us write this equation very compactly. So if I whack a G on this, I have D omega A. I can bring the G in there. the D is only seeing the forms. And so this is D, just I can write as D omega. And if I bring this to the other side, I have D omega plus 1/2 CAB C omega B wedge omega C. But that's just what I derived over here. Right, that's equal to 0 here, but D omega, then this is just omega wedge omega. So I can write the structure equation with no indices at all, remembering that omega is a Lie algebra valued 1 form. And that's going to make some proofs pretty tight. I think I give us an exercise of writing this all out with all the indices, so you can see that really we're saying some true things here. Now, with this compact form, I'm going to show you a bit more about how the connection works, because the invariance of the Lie algebra under the action of the group is easy to show. So I can do a similarity transformation by elements of the group of the generators. And then if I look at the commutators of these new objects, some similarity transformation to the generators, it's easy to see what that does, because you just write out the G, GA, G inverse with G, GB, G inverse minus G, GB, G inverse, G, GA, G inverse, so little g inverse. So the little g's, yeah, oddly enough, the little g's are the group elements, the big G's are the generators, but these just give an identity in the middle here. So this becomes G times the commutator of the original G's, which is now something I can pull out the structure constants, which happily are constants. The group doesn't pay any attention to those. Then we get a GC here, G inverse. These constants just come out, and G, GC, G inverse is G tilde, G, C tilde. And so we have that the commutator of the new generators has the same structure constants and gives us the new generator on the right. So the Lie algebra, the Jacobi identity also works. That's just made up of commutators. The commutators are the same, so the Jacobi identity is satisfied too. So I can act with the group on the generators, and it preserves the whole Lie algebra structure. Nice stuff about group theory. Okay, so the question is, what happens to the connection, this Lie algebra valued 2 form, and the Maurer-Cartan equations? And they're not quite directly invariant in the same way, because if I look at, just let's look at d omega. All right, now that's going to be this Lie algebra valued 1 form. And so if I try to put G tilde in here, I'm going to pick up derivatives of the group elements. So something else is going on with the Lie algebra valued 1 forms. What's going on turns out to be really cool. And I will just make the claim and demonstrate that it works. What happens with the omegas is that they change by a similarity transformation, but with an extra term, minus dg G inverse. And you recognize this form as the way that a connection transforms. Okay, so let's prove that that actually works. And if you do it without any indices, it's a lot shorter than if you do it with all the indices. So I'll let you do it with the indices. I'm going to do it this way. But I'm not actually cheating. If I compute G omega tilde plus omega tilde wedge omega tilde, right? This is the Maurer-Cartan equation. I claim that that equation is invariant under this transformation of the connection. So we substitute in, we've got to take D now of all this stuff, G omega G inverse minus DG G inverse. And let me just, plus all of that. Wedge with itself. G omega G inverse minus DG G inverse. And now we just work it all out. I'm going to pull the equal sign back so I have a little more room to write here. So this is going to give us dg omega G inverse plus G d omega G inverse. This is a one form, so we get a minus G omega D of G inverse. That's D of the first term here. Then D of DE is always 0. And now I pass a one form, DG is a one form, so I'm going to have plus DG wedge DG inverse. And now I've taken D of that messy form. Angle okay here. Okay, now I wedge together all this stuff. So I'm going to have, let me go ahead and make some simplification, because these things wedged together are also multiplied as group elements. So this G inverse is actually combining with that G, and it's going to give me 1. So for the first term here, I get G omega wedge omega G inverse. That's nice. That's getting the form back that we want. Then this with the second term will take a little bit of work. G omega G inverse DG G inverse. And those are all multiplied as group elements. Then this term, a G inverse G is going to go away. And we have minus DG omega G inverse here. And then finally, plus DG G inverse DG wedge DG G inverse. Okay, now we want to simplify this. A bunch of things cancel. Let's see. Now, first, those two give us just what we want. So I should have written this all way over here. D omega tilde plus omega tilde wedge omega tilde is equal to itself, is now equal to G d omega plus omega wedge omega G inverse. That takes care of the two underlying terms here. Now, what else have we got? Let's see. This one cancels that one. That's nice. Now to get these other things to cancel right, we've got to do some integrations by parts. So let me move up to this corner to do this little side calculation. Yeah, question. Was there a question?
That was just Guillermo's phone vibrating.
Oh, okay. Yeah, I wasn't looking. Okay,
Sorry about
so yeah. DG wedge DG inverse, that's this term. And I want to compare that to this term. Again, all the grouped elements here are multiplied. So I have in the middle of this, I have a G inverse DG. I can write that by the product rule as DG inverse G minus G inverse DG. And because that's 1, that derivative is constant. So I basically integrate by parts with a minus sign. I throw that D over onto the D inverse. So I get a minus DG wedge DG inverse, and then this G and that G inverse. And so these give me 1 and those two cancel. So this term cancels that term. Then we just have to work on this remaining one here. We do pretty much the same thing. Let's just look at that term alone. G omega G inverse DG G inverse. The same integration by parts here. I can write this as minus G omega DG inverse GG inverse. So I get minus G omega DG inverse. And that I hope is
Yeah, because you got the minus sign in front of it, in front of the term.
there's a minus sign. So minus this is plus that, and those two cancel. So let's cancel those two. And we got it. That's all there is. And we've shown that this transformation of the connection leaves the Maurer-Cartan equations invariant. You could prove it the other way. It's an if and only if thing. Now, this is all before the gauging. Okay, the gauging, in the sense that I use the term, you'll find a lot of physicists who, by gauging, mean they've got a specific action. They muck it up until it's gauge invariant under a local transformation. When I talk about gauging, what I mean is that it's changing the connection in the Maurer-Cartan equations, right? That subject to the condition of integrability and horizontality of the resulting curvatures, that keeps the fiber bundle structure intact, but gives you a non-trivial field strength and or curvatures to your model. So that's the gauging. That's what has produced a non-trivial field theory with whatever that local fiber symmetry is. So it's that quotient that then adds something to the side of this. So instead of d omega plus omega wedge omega equals 0, it's going to be some kind of a field strength here. It's going to be a Lie algebra value 2 form. If the Lie algebra happens to be Lorentz, then we have the Riemann curvature tensor in an orthonormal basis. If this is SU3, then we've got 8 fields here, the field strengths of the gluons, and so on. Just depending on what group you've used, you will have generated the curvature by requiring F. All right, so what is this F? It's still the algebra valued. This side's the algebra valued. So you've got, and you've got a 2 form. You've got a generator here, and you've got let's just use a coordinate basis for the two forms if we like. We could use an orthonormal basis as well. And usually a half here with the two form is a conventional combinatoric normalization. You're double counting here. You're summing over all alpha and all beta. So you're counting each of these fields twice. So it's natural enough to use a half. We've just introduced a whole bunch of fields by that change, but requiring it to be horizontal, where these dx's or the e's are a basis in the cotangent space, right? So they're not a basis in the full group. They're horizontal. That's what preserves the fiber bundle structure. Then this satisfies an integrability condition. If I take D of this equation, it's got to be true. It was automatically true here. For the original Maurer-Cartan equations, I forget if I went through that last time or not, but if you take the exterior derivative of the Maurer-Cartan equations, you derive the Jacobi identity. Right. So the integrability condition for Maurer-Cartan is the Jacobi identity. You still have that condition if I take D of this equation, but what happens, let's see if I can do it without any indices. Might work. So if I take D here, I get D squared omega plus D omega wedge omega minus omega with B omega is df. And now I substitute for D omega here. This is 0 automatically. Then I have F minus omega wedge another omega. Then here, a similar thing, omega wedge F minus omega wedge omega, all equals df. And you see what happens is, remember these have g's on them, so that's not 0, but it's just the negative of this. So those guys cancel those. That's the Jacobi identity at work. That's what we would have gotten from the regular Maurer-Cartan equations. So if you put the g's in and work it all out, you're rewriting, it's a 3 form. That's that triple anti-symmetrization you have in the Jacobi identity. And you'll see if you expand those, that's exactly what you get. The other thing you have though is that df minus f wedge omega minus omega wedge f is 0, and that is the covariant exterior derivative of f. Once again, if you work out all the group generators and things. I worked through that last time in detail, so it's already in the preceding notes and lecture. I don't want to, the point of all this is to show you that these omegas really are a connection. I just erased the transformation law, but they have that same inhomogeneous part to the transformation, a similarity transformation minus dg g inverse. dg g inverse is always an element of the Lie algebra, and that's the thing that makes it a connection. That's exactly the thing you have to subtract to have local G transformations. So let's see, and then so you use this to define a covariant derivative, and I go through that in some detail. If we've got an element of the Lie algebra that's a vector, so some element V can be expanded in the basis of generators, and we can transform that then. Let's see. I have to think how much of this I want to go through, but yeah, there's not so much. Yeah, let's say what needs to be said here. Okay, so some element of the Lie algebra, some vector. In the simplest case, we can define a V prime as a group element just acting on V, depending on the representation here. But and then we have a connection that we know transforms as G H, G inverse minus DG, G inverse. So we can use these to define a covariant derivative. And what we do is we define d of V to be the usual dV plus H. So we can just check. We can check that this is a derivation. I do that explicitly in the notes. It's linear. It's Leibniz by definition. If I take the product of a couple of vectors, I need it to be Leibniz. What that means is that basically if this were some rank n tensor, I would have n copies of H on each index here. The usual kind of thing for a covariant derivative that makes it satisfy the Leibniz rule. But the main thing I want to work through here is that this really does work. So if I write d prime of v prime, that's going to be d of gv plus h prime is gh g inverse minus dg g inverse on gv, and so I get dg v plus g dv plus g h, g inverse g just gives 1 times v minus dg, and then g inverse g gives 1 and v, and the dg parts go away, and we just have g acting on the covariant derivative. So g d v. That's our statement of covariance. Oops, sorry. There you go. That's what we mean by covariance. D prime v prime is g of dv, which we could write as dv quantity prime if we want to get fancy with our primes. Okay, so a bit about covariant derivatives. Let's see. So that's covariance. You can do all of this with indices. It still works. I've done it. It's probably good practice. I don't know if let me. Oh, yeah, I've got it there. Exercise. Rewrite this derivation, putting in all of the indices. So that'll help convince you that this actually is right, what we're doing. But you'll also see, get more familiar with working with this kind of notation. So, do that if you're interested. Now, let's see, everybody good with the board? I'll tip this up for a minute. Okay.
When will you be updating the QFT book? Just because the current one definitely doesn't go that far.
Yeah, sorry. I should just do that right after class today.
Right.
Yeah, I had meant to get it up yesterday and didn't. But yeah, I've got like a whole nother chapter on flavor. So yeah, I want you guys to be reading and working with that. So let's talk a little bit about the use of symmetries, like say circular symmetry, SO2. And I just want to point out that there are lots of uses of SO2, bicycle wheel, gears, clocks, orbits of planets, orbits of stars. And these things are not necessarily related, except that they involve circles, and everything imaginable depends on circles. So you're going to find sines and cosines in a whole lot of different, somewhat unrelated or only moderately related phenomena. The same thing is true of SU2 and SU3. So you have seen the use of SU2 in describing rotations of real 3 vectors represented as 2-dimensional Hermitian matrices. Just flag me down if you need a reminder of any of that. Happy to talk about SU2 anytime. That's and there's plenty I've written on that in earlier parts of this book, or the gauge theory stuff. But we have at some point explicitly worked through and rotated a real 3 vector by treating it as a traceless Hermitian 2x2 and acting on it with SU2. That's one application of SU2. But anytime you have a 2-dimensional complex space, if it has an Hermitian inner product on it, then SU2 is going to be a symmetry. And that happens in at least 2 more places in particle physics. So let me just describe those and caution you to recognize that these are completely different from spin, right? This is not spin we're talking about. It's just some complex 2 space that where we can define an inner product. And so we have this symmetry. The most fundamental one, which we're not going to jump to right away, is SU2 gauge theory. And that's, let's see, that's looking at isospin. The unfortunate naming here is exactly the confusion I'm warning you off of. It's not spin. It behaves like spin because it transforms under SU2. It is a property of fundamental doublets. So we have the up and down quarks, or we have the electron and the electron neutrino. These things come in pairs, and they come in pairs because, well, let's see. There are, basically for fundamental particles, there are two states of this isospin property, and so there's an SU2 symmetry. There's an inner product of these. You can actually do an SU2 rotation on all of these doublets, and it's gonna let you write U and D as or U prime and D prime are going to be some sine and cosine rotation of the old U and D, right? And the theory is going to look the same. The theory is going to tell you the same things because it's a local gauge symmetry. Of course, we have spin. So we understand that. The other place is flavor. And let's say flavorish, because here it is not an exact symmetry. All right, it's a symmetry that allows us to identify the various particle states that we expect to encounter But it's not an exact symmetry of nature. It's not a fundamental symmetry. It's not a symmetry of the nuts. Hang on, I've lost you all. There you are. Okay, good. Jeez. Let's see. Okay. Flavor symmetry is approximate because it treats the quarks as having equal mass. I think when we first started laying out gauge theory the old way, I introduced a multiplet of different spinners. And if they have the same mass, you can rotate them all into one another with impunity. Well, you can't really do that because the mass of the U quark is different from the mass of the D quark, is different from the mass of the S quark. Let's actually look at what they turn out to be. The mass of the up quark is about 2.16 MeV. And the mass of the down quark is about, I've got these in the notes, it's about twice that, 4.67 MeV. I've got all the errors on these things written out in the notes, and I strongly encourage you to go. I've put a live link to the particle data group, and if you, well, consult it regularly because it is mind-boggling. You know, you look up mesons, and they've got 100 pages listing all the properties of all the mesons that anyone has ever looked at. It's really an extraordinary collection of just how much we know about the world. Here, let me give you one example. I won't write all the deviations of these things, but let's take the K0 meson. The mass of the K0 is, oops, 6.7 plus or minus 0.16. That's the okay. So we know the mass of that meson to to what tens of keV. Another example. Yeah. Okay. The mass of the proton. What's the mass of the proton? 938. You're used to. But how about the 272081? And that is plus or minus. Let's see. What's that? 6 parts per million. We know these things incredibly accurately, and if you want to know the spins or one of the things that's tabulated in the particle data group are the decay modes. Any excited state. Now, as far as we know, the proton is completely stable, but if you look up in the particle data group, it'll list the various experiments that have put limits on the proton lifetime. And it's known to be, by some experiments, greater than 10 to the 31 years, by other experiments, as much as 10 to the 33 years. It's extremely stable, but you can't overprove it's totally stable. And, let's, I don't know, message in the sky, the proton is totally stable. Okay, maybe that, but I just want to stress how much there is that we really know about all this stuff, and we know it because, in part, because of the standard model. We have a very good description. Everything's always a model. There may be another way to do this, but compared to the number of predictions the standard model makes, it requires very few bits of input. So that said, let me back up to what we were talking about here. Let's see, the S quark, or the mass of the S, is about 93. MeV. Well, these seem like big differences until you remember that the LHC is operating at something like 14 TeV, which is a million times bigger than an MEV. So that this difference in masses is completely negligible. If for a high energy experiment, you can set them to 0. We did that when we did some field theory calculations, right? We set the masses to 0 and incurred only pretty small errors. Now, if you want to get significant figures like this, well, yeah, you don't neglect the mass. But for many purposes, we can treat the quarks on an equal footing and ask what kind of symmetry governs what kinds of particles we actually are likely to see. So you know the basic story, right? A meson is a quark-antiquark pair. A baryon is a combination of 3 quarks. There are actually, quasi-bound states. Recently, they've seen 5 quark combinations, and there are probably 4 quarks and an anti-quark where you've got some loose affiliation of a meson with a baryon, but the strong force has held them together longer than 0 time, and you detect that as a 5 quark state with a very short lifetime. But almost all the particles we see, the heavy particles, the baryons, are one of these types of thing. And so with these masses being so small, now if you go up to the charm quark, that's about what is the charm quark I've got here? Yeah, a bit over a GeV. That's more massive than the proton. So if you try to, from fundamental principles, derive the masses of these particles using the gauge theory, your results will be off if you assume that there's a symmetry between these. But if you just want to know what mesons and baryons you're liable to find, group theory is really handy. So you can think of up, down, and strange quarks as being a triplet under SU3, and you can look at the irreducible representations of SU3 to understand all the different ways those might combine. So this can be done at a number of different levels. And the lightest level, the way to just get the counting of the number of states, it's called Young tableau. So let's take some time and learn about Young tableau, because we get to draw all sorts of boxes and it's fun. What we're doing here is, suppose we've got, SO3, just 3-dimensional rotations. We've got some 3 vectors, I = 1, 2, 3. And what we want to know is what happens when we make combinations of, say, 2 or 3 of these. Now we know how that if this transforms with one copy of an SO3, an element of SO3, this is going to transform with 3, like any rank 3 tensor. But this is reducible, and the reduction we're talking about here is actually quite simple. It's symmetric and anti-symmetric parts transform independently. If I've got, say, ui vj minus uj vi, that's some matrix, mij. It's clearly an anti-symmetric matrix. If I do an SO3 transformation, it would be, I get a new M, and that's the transformed version of M. It's still going to be anti-symmetric. No SO3 transformation is going to make an anti-symmetric thing symmetric. And so that's an irreducible part of this higher order object. All right, so we want to be able to find those. And it's nice to be able to find them quickly and easily and know how many there are. And that's what Young Tableau do for us. It's just a cool way to count. So here's what we're going to do. Let's write one of these as a box. And since it's three-dimensional, I'm going to put a 3 in the box. Now, if I put two of these together, then there are going to be 9 states. 3 times 3, that's 9 states. But they're not irreducible. I can symmetrize or I can anti-symmetrize. So what I'm going to do is I'm going to say, okay, to anti-symmetrize, I'm going to write one above the other. And to symmetrize, I'm going to write one next to the other. And Young presumably figured this out. And what you do is you write a number in each of these, but when you anti-symmetrize, you're always starting with a 3. But anti-symmetrizing, you drop by 1 each time you go down. And symmetrizing, you go up by 1 whenever you go down. All right, and following those rules, you can easily figure out how many components there are in the anti-symmetric and the symmetric parts. Here's how it goes. The number is a ratio of a numerator to a denominator, and the numerator is the product of the numbers. Okay, so the numerator here is 6 and the numerator here is 12. Easy peasy. Now, what's the denominator? The denominator, well, we've got some figure here. Right? Let's say we're working with the anti-symmetric thing like that. What you do is you imagine an arrow coming in from the right and turning in each box. So you're going to have one arrow that comes here and turns in that box and goes down. You're going to have another arrow comes in, turns in that box and goes down. Now you just count the number of boxes the arrows went through. This one went through both boxes. That one only went through 1, and the denominator is the product. 2 times 1 is 2. So the number of anti-symmetric states, so the count for anti-symmetric states is going to be, right, n over d is 6 over 2, 3. So we expect an anti-symmetric matrix in 3 dimensions to have 3 independent components. You already knew that. No new information, but you see how this works. Let's try the symmetric. Okay, so we've got a 3 and a 4 here. We bring an arrow in and it goes through 1 box. We bring an arrow in, go a little further, and it goes through 2 boxes. So now we get 12 over 2 is 6, and hey, that's right. That is the number of components of a symmetric 3 by 3 matrix. Right now, yeah, question.
Is that not just going to give us factorials all the time? Or the denominator is going to be a factorial?
Yeah. You can see the combinatoric factors emerging. The trick is it gives you the right factorials, and you don't have to think about it. I have thought through this like ages ago, and I actually convinced myself that this is giving the right combinatorics. And I invite you to do the same. But before wrestling with that, learn the technique, because it's useful for a whole slew of different things. Let's look at some rank 3 tensors. So now suppose we take UI, VJ, WK. Right now we're talking about 27 different states. What are the irreducible subgroups? Well, we can symmetrize this pair or anti-symmetrize that pair. We can symmetrize these or anti-symmetrize those. There are various things that could be done here. This lets us keep track of them. So let's just do this one. I'm going to give you enough examples that you know how to do this. And then I've written out half a dozen exercises, all easy, all kind of drawing a bunch of squares and stuff. But let's look at 3 by 3 by 3. The technique here is to do 2 of them first, and then combine the others. So let's take these first ones. We saw that we could get an antisymmetric 3-2 plus a symmetric 3-4, and all of that we're going to take times another 3. So got some more rules to follow here. You're always pushing up and to the left, which I mean rows that are higher in the diagram are always equal length or longer than rows below. Columns to the left are always longer or the same length as ones further to the right. So if I bring another 3 into this block of 2, I can do it in two legal ways. I can lengthen that top row, that gives me a 4, or I can drop it below and lengthen the column. So I have 3, 2, 1. I cannot attach it down here. That's not allowed. So that's what happens if I bring this 3 into that. Now I bring a 3 into this one, and I can stretch the row. I get 3, 4, 5, or I can add a row as long as it's shorter. So I can do a 3, 4, and then a 2 down there. So that should give me all of the 27 states of a product of three vectors. Well, let's see, because it had better add up. I'd better still have all the states here. So this one, I'm going to have 4 times 3 times 2. Just multiply the numbers. And then arrows coming in, I have a 1. Here I get a 3. And here I just get 1 again. So I'm going to divide by 3, and that's equal to 8. The 3's cancel. So 8 of the states have this symmetry where I've anti-symmetrized the first 2 and then symmetrized the third. All right, let's try this one. Where I have 3 times 2 times 1, but I get 1 times 2 times 3, bringing the arrows in. So this is a singlet. There's only one totally anti-symmetric state. Well, anti-symmetrizing 3 indices in 3 dimensions, there's only one way to do it. So that makes sense. Here, I have 3 times 4 times 5 divided by 1 times 2 times 3. And that gives me 10. So there are 10 states that are totally symmetric. And This one, well, this is going to be 8 again. So there are two independent irreducible representations with 8 each. There's a 10 and there's a 1. A singlet, 2 octets, and a decuplet. The let's see, one other example. Let's see. I don't know. Maybe it's enough. I do 4 here in the notes. You want to see another example? Let's see. Oh, yeah. Let me do one further because yeah, it gets a little. Well, not a modification. You just have to realize how to follow the rules. So if I have 4 of these, now there are 81 states, but let me just draw them. So here we can lengthen that top row, or we can add it here. We're allowed to have 2 rows the same length as long as the top is greater or equal. So we can have a block of 4, or I can anti-symmetrize and put one that way. So I'm adding the block below. Now, anytime you've got a full column like this, it doesn't count because that's a singlet. That doesn't change the numbers. So for most purposes, you can just ignore that. And this is going to be a 3. Let's see, what's this block? We have a 3, 4, we have a 2, and now we go up to the right. So as you move to the right in a given row, you add 1 each time. So this is 4 times 3 times 3 times 2. And then there's a 2, a 1, a 3, and a 2. 2, 1, 3, 2. If I did that right, and that makes it a hexaplet, 6 states. And yeah, there's no particular magic. Let's look at this one. I can add a block to the right, or I can add a block below, but I'm not allowed to have 4 blocks down, and the numbering takes care of that. At 3, 2, 1, I'm down to 0. So they're not going to be. There is no way I can anti-symmetrize 4 things in a 3-dimensional space. And that's really all there is to Young Tableau. But I find I use this all the time. All right, let me just read through the exercises. You can probably do them as fast as I read them to you. But so yeah, carrying out the counting in the 3 and 4 cases. All right. All right. Use Young Tableau to find the number of components of symmetric and anti-symmetric tensors in n dimensions. So do it with a general n. You put n here instead of 3. You put n plus 1. You put n minus 1. And you do the counting. You can do it for any n just as fast as you can do it for 3. Okay, so how about general relativity? The Christoffel connection is symmetric, right? It's not the most general connection you could write. The most general connection you could write is 4 by 4 by 4. What are the irreducible subparts of a connection, the most general connection? The symmetric part gives you non-metricity, the anti-symmetric part gives you torsion, and then the symmetric part gives you the Christoffel tensor. So a question like, how many components does the Christoffel symbol have in 10 dimensions or n dimensions? You can quickly answer questions like that with this stuff. Okay, here's another example. The 2 electrons in helium. All right, each can have 2 states. So you're looking at 2 times 2, right? There are 4 states total. What's it break into? I'm going to do one of your problems for you because there's a conclusion that's kind of cool here. So I take a 2 by 2. And all right, so we can make it anti-symmetric 2, 1, or we can make it symmetric 2, 3. And this is going to be 2 times 1 over 1 times 2. So there's only one anti-symmetric state, a singlet. Here we have 2 times 3 over 1 times 2, 3. So there's a singlet and a triplet. Well, what are those? Those are ortho and perihelium. The triplet is the symmetric state. The singlet is the totally anti-symmetric state of the wave functions. The wave function is a product of the two, and it can either be the spins, aligning or anti-aligning. There's a symmetric or an anti-symmetric combination. The total wave function for fermions has got to be anti-symmetric, which means that if I take the anti-symmetric combination here, that singlet state is going to have an anti-symmetric spatial wave function. And an anti-symmetric, wait a minute, I'm saying it wrong. This is anti-symmetric, so the singlet's going to have a symmetric wave function, which allows a non-vanishing field at the center and gives a fairly high potential. The symmetric state must have an anti-symmetric spatial wave function, which keeps the electrons further apart. So the triplet state is the lower energy. And I always forget which is orthohelium. The triplet is called orthohelium, and that's the ground state of helium. So predictions, it's surprising, and it continues to be surprising to me how useful it is to just know how to do these. So work through these examples, get familiar with Young tableau, and have fun drawing squares and thinking up different ways you can use it. Any questions? Are you clear on the rules? Again, I'll post these notes. It's the first chance I get here soon. So it'll be good through this chapter. What's next? How are we doing? Let's see. Yeah, good. We've got time. The next thing I want to talk about is the standard form of Lie algebra. So this takes us a little further than the Young tableau. The Young tableau tells us how many particles to expect. So, for example, let's just look at an up and a down quark. If we're talking about an up and a down quark, well, we've just done it. This can be either the up quark or the down quark. So what combinations do we get? Well, there's a triplet state and a singlet state. And let's see, what do those correspond to? Well, let's multiply out the wave functions and see what those look like. So let's see, what are we combining here? Yeah, we're taking, I'm not sure I'm doing this quite the right way. Because I want to look at the up and down quarks, but what I'd really like to talk about are the mesons. So, let's see. What are we going to get? We're not really talking about the same twos here. And I have to think a second about how I would represent the the anti-quarks. Yeah, it seems to me that seems to me that what we're really talking about is a tube with a 2 bar. But think how about how you do that? If I just looked at symmetrized and anti-symmetrized states, let's see, I could have a, yeah, all right. I can have a, yeah, this works. This works. I can have a UU bar, or I can have a UD bar plus a DU bar, or I can have a DD bar. And that's a triplet state. If you've worked with Clebsch-Gordon coefficients, raising and lowering operators to find the different spins, you start with the highest state and you lower and you preserve the symmetry. There's also a singlet UD bar minus DU bar, and those are the 4 combinations of quark bar, and they fall into a singlet state and a triplet like that. So we can count quark states pretty quickly here, meson states pretty quickly. Now, as I say, to go further, it really helps to have a standard form for Lie algebra. So let's talk about that next. How are you guys holding up? You need to stretch? You good? All right. Everybody's happy? All right, good. So let's suppose we have a Lie algebra. Yeah, so if you find yourself doing those problems on the Young Tableau and you run into a question, just email me, and we can iron out the details quickly. So Lie algebra, we've got generators, product, structure constants, and all of that. So yeah, Cartan came up with a systematic way of describing Lie algebras and Lie groups, and did all kinds of stuff with it. But basically, we want to divide the generators into 2 groups. What we want to start with is a maximal commuting set. Set of generators. Now, for SUN, the generators are traceless Hermitian matrices. So how many are there? How many commuting generators are we going to find? It's the same as the number that we can simultaneously diagonalize. All right, they're all traceless. So there are n diagonal elements, but they all have to be traceless. That removes 1. So n minus 1. So we should have n minus 1, and we'll call those h's. So we have n minus 1 commuting generators, and we don't expect to have any more than that. Couldn't have any more than that in an n-dimensional representation. So yeah, I do that a lot too, Guillermo. Your fingers sore? mine get really sore sometimes, especially when I'm typing on this book all day. It's yeah. Okay, taking a breath here. what we can do for the other ones. And yeah, we'll figure out that we'll show that we can do this. For the others, let's say choose the rest. To satisfy. So the commutator of HI with let's call these E alpha. E alpha. You want to choose them to satisfy this kind of a relationship. You want the commutator of the H's with each of them to return the same generator. And it'd be nice to see that that's actually possible. Turns out it is for simple groups. Maybe semi-simple, never quite clear on when you can do one or both. Semi-simple is probably almost the same, but what does this mean? Let's choose any basis and let H be yeah, let me just work at one. So H is some linear combination of the G's. And let's pick an E and let E be some combination, some other combination of the G's. Then we can work out the commutator of H with E. And what is it? Well, we get these just the linear combinations, and we're going to have a GA with a GB here. And then we're going to get a structure constant. And we would like for that, we're going to demand that that be some rho times E again. Let me write it with a C here. So we're gonna require that to satisfy this relationship. Well, what is that saying? If we let MAB now, wait, let me fix my indices here. Let's call it CB. Be a matrix defined by the contraction of A. Now A is fixed. We can find the diagonal ones. So in terms of any basis, we know what the A's are. Then with the structure constants, CAB, it's like an adjunct representation. But then if I write this equation, what it says is that this matrix MCB acting on this linear combination that gives the E's has to be rho times BC, where I'm dropping the G. I've got GC on both sides. That's an eigenvalue equation. That eigenvalue equation always has solutions for simple groups. The basic property, or one way to characterize when a group is simple, is that the structure constants give you non-degenerate matrices. And so let's see. Yeah, one criterion is that you have a non-degenerate killing metric. Yeah, I was going to write this out. So if I take C ABC times C CDA, contract it this way, that gives me a symmetric matrix KBD. Symmetric because I'm just doing it with two C's. This is equivalent to taking the trace of a product of two generators. There are lots of ways to define what's called the killing metric. But if this is non-degenerate, that's one sign that the group is a simple group. Basically, a group's being simple is a non-degeneracy condition on the structure constants. So given a suitable non-degeneracy of these matrices, we can always find some B's that do this. So we can find E's that have this property. And, there are a bunch of theorems about this stuff. I don't know, any of you, read any good group theory books that go into this? I haven't in a long time, but, there are theorems about all this, exactly, what sort of groups have these properties and so on. But we can do this, and we'll see that for the unitary groups, we can definitely do this all the time. So that gives us two sets of properties. Let's put them up here. So we've got a bunch of commuting H's, and then we've got the commutators of H's with the remaining generators, E alpha, and you've got some basically eigenvalues rho I alpha and returning E alpha. The only other thing we need is E alpha with E beta. And it turns out that, I hope you got it. You okay here? I just erased our eigenvalue equation. Okay, so how can we get at this? Actually, the Jacobi identity tells us something about those. If we look at H acting with the commutator of two E's, then we cycle these, so we have E alpha with E beta with H I plus E beta with H I with E alpha. All of that has to be 0. But we know that these give E alphas back. So this says that H with the commutator this is going to be minus rho I beta and give us an E beta back. Just flip those and we're back to this form here. So minus rho beta I, then E alpha with E beta. And then this one that's just going to give rho plus rho I alpha with the commutator of E beta with E alpha. All that still has to be 0. So bringing some things to the other side, the commutator of H with the commutator of two E's is going to be, right, I want to flip this so it's an E alpha E beta. And I bring them to the other side, I'm going to get rho I beta plus rho I alpha times the commutator again. So that has this form. So we've closed back into the E's. And if you dig into this deeper, you can order the E's. It turns out that they come in pairs. Notice that if the sum of these two eigenvalues vanishes, then you get 0 over here, and H commutes with that, so that means it's an H. So if rho I beta plus rho I alpha equals 0, then E alpha E beta is some kind of an H. Maybe a linear combination of the H's, but some kind of an H. If otherwise, E alpha E beta is it somehow lies in the space of e's. So you're going to get one of these or the other. So either H or E, not both. And it's easy to see when you do get one. And these things do come in pairs. So if I've got some E beta, there is some other E such that this is 0. The eigenvalues come in opposite sign pairs, and we'll see that happen even with the simplest examples. So this is what we mean by the standard form of a Lie algebra. This is what we've done this like amply with SU2, right? And I'll run through it, but look at what this implies about rotational motions. Everybody got this? So what we want to do is label states with what? Finding another marker here. With the eigenvalues of the H's. Let's say lambda 1, lambda 2, lambda, how many? Big N minus 1. So we've got a bunch of eigenvalues here. So that HI on, let's just call this the lambdas, is going to be lambda I, like this. So we can find these guys, right? Now, okay, Mo, can you share it? I can't hear.
Yes. Yes. What was that?
Oh, something was very funny there. I just wondered if it was something you could share or something you could definitely not share.
Oh yeah, I mean, yeah, I won a game with 0.3 seconds in chess, and I thought that was pretty funny.
Oh, 0.3 seconds. That's very fast.
Well, you can pre-move, so
Okay.
the guy just moved wherever, and I just moved, and I technically won. So I thought that was pretty funny.
Yeah, that's like, you know, what, chess with plaid, right?
Chess with plaid? What's that?
Plaid.
Is that like a software?
Like a Tesla. The Tesla plaid can go
Oh,
0 to 60 in 1.9 seconds or something.
oh, sure, yeah.
Totally absurd.
Yeah. The funnier part
So-
was that I hung my queen and then he hung it. So we were both just going crazy. We were both bad.
Oh, geez.
We were really bad. But that's why I was laughing, because
Just plaid. Cool. All right. Now, good going. All right. So, all right. So now look at what happens if I let H act on E. One of the E's acting on lambda. All right. These have just the form of raising and lowering operators. You know, stepping by these weights. These are called weights. So we know how to do this, right? We write this in the opposite order on lambda, plus the commutator of H with E alpha acting on lambda, and that pulls out a lambda I. And this commutator, voila, rho I alpha times E alpha acting on lambda. And so we collect things here, and we see that we still have an eigenstate So this thing we've always done with spin and SU2, works for any simple Lie group, right? So H acting on this compound state, whatever that state is another eigenstate with the eigenvalue increased by rho I alpha. And so we can step through the whole panoply of possible states by acting on any eigenstate with all of the different E's. These are just raising and lowering operators. Well, you know that J plus and minus, right? Or like JX plus or minus I, JY. Those are raising and lowering operators. And notice they do come in pairs, J plus and J minus, with what? J3 with J plus or minus. It's going to be plus or minus probably H bar over 2 if we're keeping track of units times J plus or minus. So the thing we do with SU2 is exactly this. And oh yeah, they come in pairs. So we'll see explicitly that they come in pairs like that when we do the SUN. It all works the same way. So yeah, there's a oh boy, I was lucky. I just hit the off button on my computer. It didn't go off. That's a good thing. I just grabbed it by the corner and whoa, that button should be somewhere else. Okay. So we want some systematic language for all this. What we do is we let the HIs form a vector. Like this. And so we're going to have a vector of rows for each alpha. All right, so this will be row 1 alpha up to row n minus 1 alpha. So these are called root vectors. So you take the weights, you form a root vector. And then you plot the root vectors. And this is called a root diagram. And because these things come in pairs, there's always an opposite one here. And if you choose the normalization of your H's right, you can make all those vectors the same length and equally spaced and make them look very nice. And then when you look up in Wikipedia, what it says there isn't quite so crazy. It gets a little formal, but it's just raising and lowering operators, right? And they you scale them right, and they have this nice property where you basically form some sort of polygon out of these guys. And by applying E's, you're basically stepping your way through this graph. Now, these things, for SU2, it's just a one-dimensional graph. You're just stepping your way along a line, either up or down, raising the spin or lowering the spin. If you've got an electron, there's only one step and you're done. But if you have a system of electrons, then they can add up, and so you can keep going. For SU3, N is 3, so there are 2 diagonal elements, and these things span a plane. There are different directions in the plane that you can go by acting with an E1 or an E2. We'll do that explicitly. The higher order groups, maybe you've seen this pretty picture that people draw of E8. It looks like a flower. Have you seen that? Here, I'll share my screen. I'll pull one up. Yeah, here's one of them. If I can figure out how to share my screen. Uh-oh, I've lost you guys again. Share screen and share. Allow Zoom, yeah. Oh man, open system preferences. Let's see. Don't know how to do this. Oh, rats. Okay. Zoom. Oh, wait, there. All right, here's Zoom sitting there. But huh. I don't see how to do this. It's shaded out. Oh, there. Oh, click the lock to make changes. There we go. All right, Zoom. Oh, it says quit and reopen. I don't want to quit and reopen. Okay, so next time I can show you a picture. Meanwhile, just Google E8. Or Petrie. Yeah, E8 Petrie, Petrie. And yeah, so, oh no, then yeah, what you want is E8 polytope. I've linked it in the notes, but you can at least see some examples there of how complicated this gets. I'm going to quit fussing around before I lose you all. I have to relearn how to use computers when you get a new one here. Now, where did my notes go? Oh, geez. Ah, there. All right. So, yeah, Google maybe E8 images. You know, look at images of E8, and you're going to see this thing. You know, E8's got, what is it, 252 generators or something. So I think the root diagram is, well, it's at least 8-dimensional, and you know, very hard to draw. So you can look at various projections of it and stuff. So for big groups, you know, mostly it's a pretty picture that you gawp at. But for groups like SU2 and SU3, it leads to something called the eightfold way, which maybe you've heard of. Let's see now. I don't know. It would probably be boring to talk more about SU2. Let me see if I can talk about SU3 a bit. For SU3, or do you want to see this for SU2? I think, okay, it's J plus and J minus. J3 is the diagonal one, and you can just raise or lower. So it's a one-dimensional picture. You know, I don't think it's worth our time to go through that. It's in the notes. You can quickly read through that. Now in, what one was it, 62, Murray Gilman wrote a book on the possible states of, I think he was talking mostly about mesons at the time. Yeah, what is the title of the paper? I'm not going to look it up because I'll lose my place here. But he introduced 8 generators for SU3, and he based them. Let's see. Get a different marker here. And for new markers, hang on. He based them on the Pauli matrices. So now they're called the Bellman matrices. And everybody writes them down first and then immediately goes to the standard representation. But it is sort of a nicely intuitive way to think of matrices. You have all right, the first one is like sigma x, but zeros everywhere else. All right, and then you have 0 minus I. The dots are all zeros here. Then let's see. Oh, we're going to have similar things, 0, 1, 0 here, and zeros, and then I and minus I there. And then clearly we ought to have 0, 0, 1, 1, 0, and 0, 0, minus I, 0. And it's clear that we can, fill out a basis for traceless Hermitian matrices this way. So this is lambda 1, this is lambda 2. For lambda 3, though, he took sigma z, 1, minus 1, 0, that one. And then he did these other two combinations. And then there's one more. So then this is lambda 4, lambda 5, lambda 6, lambda 7. And then lambda 8 is the, you want an orthogonal traceless one, you can take 1, 1 minus 2 here. And probably a normalization. What did he use? 1 over root 3. Not quite. Oh, that comes from probably getting the right charges for the quarks. You can predict charges of particles this way. So then you compute the Lie algebra. Lambda I, lambda, or let's call it lambda A, lambda B is F, C, A, B, lambda C. The Lie algebra closes. Oh, but he's chosen Hermitian ones here, so we're going to need an I here. In fact, just like the Pauli matrices, we needed 2I. So these are not the real structure constants. And then you can also look at the anti-commutator of these. That turns out to be useful for some purposes. And all right, for these, you get 4/3 delta AB plus some symmetric thing, DABC, lambda C, and a 2. Like this. So DABC is symmetric. And FABC is anti-symmetric, totally. And you can, figure out the properties of those. I don't think we need to use them particularly just at the moment. There are Casimir operators. There are 2 Casimir operators for SU3. For a simple group, you always have a quadratic Casimir because you can use the killing metric, but basically it's always going to be just the sum of squares of the matrices. Yeah, up to normalization. Oh, wait, let me just check. I'm still working on the normalization of these guys. So I'm not quite sure what I'm going to end up using here. Yeah, lambda 8 might have a different normalization, but basically we can just sum the squares of of the generators, and that will commute with all of the others. I think that works in any basis because what you're really doing here is taking lambda A with lambda B with the invariant, the group invariant killing metric. And that commutes with everything, because if you commute, you get this F, which let's see, it anti-symmetrizes onto the K. So it's not actually too hard to prove that that's always a Casimir operator. Oh man, you guys are looking a little stony faced. How's it going? Are you holding up? I know it gets long, but it's even harder when it's hot. It's hot.
And this isn't about everybody, but I do have another meeting coming up soon, or tutoring.
Oh, what time, Kevin?
At 4:15.
4:15. Yeah. Okay. All right. Well, I'll wrap this up.
Okay.
Yeah. Yeah. The next thing to do is find the standard form for SU3, and I'm not sure I'll take time to do that today. I can write the other Casimir, because you can use these D's to write another Casimir. ABC. There's a cubic one, lambda A, lambda B, lambda C, like this, and yeah, that's basically it. It's not, there are techniques for finding Casimir operators. For SU2, there's just the one, and it's this quadratic one where you sum the squares of the polymatrices, which in that basis just gives you the identity. But in general representations of SU2, it's J squared, right? That's the sum of the generators squared, right? And so you label states by the Casimirs, and these raising and lowering operators can't change the Casimirs because all the generators commute with it. Then you label states by, in addition, by the eigenvalues of the various diagonal elements. So for SU3, we have two Casimirs and two diagonal elements. We can label all of the states by those four numbers, and by acting with the raising and lowering operators that are, they're going to be combinations of these. So just like J plus is J plus or minus, remember, is J1 plus or minus I, J2. If you take that kind of combination here, that's going to give you 0, 1, 0, 0, and zeros elsewhere. It gives you just unit off diagonal, above or below. So the minus have the one down here, the plus have the one up there. So I can form three such pairs. Lambda 1 plus or minus I lambda 2, lambda 4 plus or minus I lambda 5, lambda 6 plus or minus I lambda 7. And so we have three pairs of raising and lowering operators for SU3. And if we adjust the weights right, they can move us in opposite directions here. So here's one pair, here's a pair, and there's a pair. And we end up tracing out a sort of a hexagonal shape in the root diagram. These are going to turn into particle states. Okay, there actually are two particle states in the center here. So we're going to have a distinct particle state at each of these corners and two in the middle. It's an octet, and there's an octet for the baryons. There's an octet for the mesons, actually more than one. This is what came to be known as the eightfold way. It was a way of organizing the possible particles, the possible mesons or the possible baryons that you expect to make from 2, 3, 4, 5, or 6 quarks. You can actually do this kind of analysis even with all 6 quarks. There's not an exact gauge symmetry of the 6 quarks, but the combinatorics still work, even though they have different masses. And so we can use these techniques to identify all the possible particles, baryons and mesons, that we can build from the various quarks, up to even all 6 of them. So maybe that's a good place to call a halt here. And good. Is this a regular meeting, Kevin? Or just today? Or?
Yeah, no, I have a student I meet every Monday, but it kind of shifts around forward and back a couple hours.
Yeah.
But no, I mean, I always assume that this is going to take usually but 2 hours for this class at least.
Yeah, since we've lumped what three periods into one, technically it ought to be, I don't know, 150 minutes, whatever that turns out. So 2.5 hours. A couple times we've run 2.5 hours.
Well, I can avoid scheduling them before 4:30 then, just to make sure.
Yeah, I've now I'm going to feel obliged to come up with 2.5 hours of stuff all at once. But yeah, I won't promise. And you know, if we need to call a halt to it sooner, it's okay.
Yeah, not on my account. I mean,
but okay,
I would be able to watch the recording too if you guys.
Yeah, I think yeah, we should probably try to keep 2.5 hours free. Although you know, I'm not sure. Yeah, maybe when we start talking about string theory or doing the gauge theory, we may have some need of some, you know, the full 2.5 hours.
Yeah, well, that's not a problem for me.
But yeah, there's certainly no problem now. I'm kind of up to the end of my notes anyway.
Okay.
So I will post this stuff online, and I think let me just skim down here. That I think that I'm pretty close. Yeah. Well, I still have stuff to do on the end of chapter 13. And then chapter 14 will be the standard model. But yeah, I want to talk about the baryon and meson octets and singlets and decaplets and all of that stuff, and you know, give names to some of these particles. But that's about all that's left in that chapter. So until next week, or until you Zoom with me tomorrow again, Eli. What?
We could either do. Would Wednesday work?
Or Wednesday's fine. Yeah.
Let's plan on.
So
Wednesday.
sometime like Wednesday afternoon be good.
Yeah, that'd be good. For me.
Okay, let's figure on that.
Sounds good.
Yeah. Otherwise, see you next time.
Sounds good.
Good on.
Talk to you then.
Bye.